Hi, I'm DJ Werq. On this episode of the Cyber Gizmo, I'm going to be talking about the Holy Grail of computing. Yeah, stay tuned right after this. So when you get a 10 gigahertz computer, or a 10 gigahertz CPU rather, that is when you will achieve the Holy Grail of computing. So when did that all come about? So industry technologists and PC gamers have been talking about the Holy Grail of computing for almost 30 years now. What is it? It's a 10 gigahertz CPU. And so 30 years later, where are we? Well, we're about halfway there. Intel has their 12th gen CPU, which operates at around 5. Some of them are at 5 gigahertz, some are at 5.5. And yeah, you can certainly overclock and do extreme overclocking and get up to, 7 or 8 gigahertz. But here's the thing, though. I mean, that's not real world. Are you seriously going to take home that kind of a rig and run liquid nitrogen through it? Oh, wait a minute. I got to pour another jar of liquid nitrogen into the bucket on top of my CPU. So, yeah, while you're trying to play a game, I don't think that's very practical. So let's just say that the type of overclocking we do would be the typical one that a gamer would do at home. So they might overclock their machine up to 6.5 gigahertz, maybe 6.2, somewhere in there. There's not a lot of headroom you can do without going to, to do cooling on those chips. But, yeah, so the extreme is definitely a little over the top, right, for home use. So we always think in terms of clock speed whenever we're doing overclocking. There are other variables in there that you try to balance, right? There's memory and there's the voltage that you try to balance together to come up with something that's stable that will run for the duration of your session with the game or whatever you're playing. So, or whatever you're doing. But in the 90s, there was an interesting turnabout. And it happened, I'm not sure if it was the NEC version of the chip or Toshiba's version of the chip, but this was the MIPS 200 megahertz chip called the R10000. And the R10000 came out, it came out initially as like 150 megahertz, and then they did 175, and then finally they went to 200 megahertz. I believe that was 1996, but yeah, don't quote me. So, and then DEC had released their CPU, the 21164, and then they had the A version of it that came out about 96 as well. And that was a 400 megahertz variant of the Alpha chip. That's the one, by the way, that went into the silicon graphics machines like the Onyx and the Onyx 2. So yeah, those were the chips that were in there. And I think the MIPS chips went into the Cray TX, if I remember right. I mean, yeah, but you could get them on PCs as well. But the interesting thing about they benchmarked both of them, and they found that the results were so close that it was indeterminate as to which one had won. It was a tie. Now, wait a minute. You got a 200 megahertz CPU that's going up against a 400 megahertz CPU. That's not exactly something that you would think would happen, that one would beat the other. And then it got even better. Yeah, the IBM outperformed the Alpha 21164A in floating point operations. So why? What the heck gives here? What's going on? Well, I thought that, that clock speed was the Holy Grail. I thought that was the whole reason that we were trying to speed things up. So actually, no, it's not. Actually, yeah, it's not. The key to performance is actually a math formula. I mean, at least in predicting it. So yeah, okay, so it's two. There's two math formulas. I'm not going to go through them here. It was one of these formulas that actually predicted that once we got to 10 nanometer, 10 gigahertz CPU should be possible. Well, it took Intel a while to get to 10 gigahertz. Now, according to Moore's Law, that was supposed to happen in 2017. It didn't, obviously. It didn't until actually this year that we actually had, actually last year that we actually had 10 nanometer chips for the first time. So what is the problem? Well, the problem is the second one, and that is the power dissipation of CMOS circuits. Yeah, that's the limiter, and that's the bane of Moore's law. It's this one that prevents you from getting to a predicted value. And so, yeah, the more voltage it takes to reach a particular CPU frequency, the more heat that's dissipated, and that heat becomes a barrier, as we'll see. So, ARM has been making a lot of inroads against the PC. I mean, not in terms of sales, but in terms of performance. I don't think it's really caught on yet that what the capabilities of the ARM is. So that's why I'm here. I'm here to explain this to you and try to, not to convince you to move everything over to ARM, but to give you an alternative that you haven't probably considered. So what is going on in the design of the chip? So everything today is to go wider. We want more cores. We want more compute units or ray tracers or RT cores, tensor cores, more cache. We're trying to go wider. We go wider because we want for a given cycle, we want that CPU or GPU to do as much work as possible. A lot of it is occurring in parallel. So that's the whole idea. It's still going along. I mean, it's still going on, but ARM is still rapidly overtaking it. And why is that? You know, the interesting thing is none of the ARM processors have the threading model that the x86 has, right? So I don't get these phantom cores on an ARM. You get what you get. If you order an ARM machine with 8 cores, you get 8 cores. You get 4 cores, 8 cores, but there is none of this multi-threading model. So why are they able to do that? What's going on with these? Well, if you look at what an ARM processor is, it's simply a system on a chip. Everything is closer to the die, the CPU die, and the closer you get to the die, the less latency you have, the less interconnects you have, and all of those are factors in what limits your performance. The PC, on the other hand, now I'm not picking on AMD. It's AMD and Intel together. So they have 3 layers of cache that they use, L1, L2, and L3. There's also the PCH, and then there's the PCIe controller. You may have a SATA controller, but you definitely have a NAND controller. And then there's the biggest killer of speed of all. And that is the heat wall. And it's something that you don't hear too many people talking about. I think I never hear any of the big manufacturers talk about the heat wall. They kind of trying to ignore it. Like, if I don't talk about it, maybe it'll just go away. So what is that? What is the heat wall? Well, if you remember back when the Pentium 4 or the AMD Bulldozer or Steamroller came out, those were disasters. And it was mainly because they did not get the performance out of them that they were hoping to get. And why? Heat. It was heat. Those were, at least in the case of the Pentium 4, that was a monolithic processor. In fact, it was the last monolithic processor that Intel manufactured. So, yeah, heat. It was the disaster. They were trying to reach, I remember the stated goal for the Pentium 4 was to get to 6 gigahertz. Well, look how long that's taken, right? So I think this is from a paper back from 2013 where they talked about the factors of the heat wall itself. The black square that goes around the diagram, that is the barrier. That's the heat wall. So what is it? When we started out with the Pentium Pro, and then hit the Pentium 2 and 3, I mean, the heat went from what a hot plate would generate, and it just kept climbing for each one of those until the Pentium 4, which was pretty close to a nuclear reactor. And by the way, our processors are approaching this again. They backed it down by declocking, going to multiple CPUs. and then spreading the CPU load in parallel across all those cores. But now we're climbing back up to that point again. Once you hit that point, there isn't any practical way to cool the machine. Once you get into the temperature of what comes off of a rocket nozzle, yeah, you don't want that on your desk. Trust me, you wouldn't even want it in your house. It would catch everything on fire. The other one, yeah, of course, and then they have the heat of the surface of the sun, which actually isn't the hottest part of the sun. The hottest part of the sun is actually the corona. But anyway, that's neither here nor there. So this heat wall is what limits the ability of your machine to go faster and faster. So there's some Jay's 2 cents was talking about this in his latest video. I think it came out this week at the time I'm making this. He was talking about some of the leaks surrounding the NVIDIA 4090. And of course, yeah, every time you get closer and closer to a release of a major product, everybody's like, oh, it's going to do this, it's going to do that. They think they have the answer to what the thing is going to be. And then when Jensen gets up on stage, it's something like, wait, that's not what he said it was going to be. So, but anyway, one of the leaks, now I don't take a lot of stock of them, and neither does Jay. Jay is one of those guys that, well, I'll talk about it, but I'm not going to put too much stock in it. He even said, take this with a grain of salt, or maybe a grain of salt on top of a grain of salt. I would say, yeah, same thing. Take this with a grain of salt. But the leakers think that the power consumption for the 4090 will be around 600 to 900 watts. Wow. That would be a world's record if they do that. That's a home run. That's a lot of power being drawn by a GPU. So, and by the way, that 600 watt figure, it just happens to be the maximum draw on PCIe 5 that a single cable can deliver. And I thought that was a lot, I thought that was a lot. And the funny thing is, can you imagine the kind of power supplies you're going to need? I mean, you're north of 1,000 watts right now. If you get closer to 1,500 watts, you're going to be as close to any wall circuit in a home that you can get without having to go to 220. And in fact, with that kind of amperage, you're probably would be better off to go 220 because the amount of heat that's generated when you're close to the maximum capacity of your wire, yeah, that gets dangerous. So, yeah, and even Wendell was talking about this in his latest video on level 1, where he was talking about, wow, I got my electric bill for my servers, and man, was it expensive. I can imagine it would be. We used to talk about, and he said this too, we used to talk about, well, just get some cast-off servers and bring them home, put them in your lab, try to put them someplace where the noise isn't going to get you, because they are loud. They are meant for data centers. But, the thing is, when you're buying cast-off servers, you're probably getting servers that are at least 4 years old, maybe even older. And those were not the most efficient ones, and they didn't have the most cores in them. So what you're buying is a machine that generates a lot of heat and uses a lot of power. So for very little computational gain. So Wendell was questioning, do I really need all that computational horsepower at home? Can I get by with less and therefore lower my electric bill? And yes, indeed, he could. He showed a couple of examples, but Wendell's married to Intel and the architecture for x86. I'm not. So I've been well, I'll talk about it. But so what do we know for sure here on the heat wall? Well, raw clock speed is a dead end. You're not going to be able to get through the heat wall with that. You're going to hit the heat wall, and that's it. You're not going to go any further. And performance per watt, we know, doesn't scale with clock frequency very well. We know that. The Pentium 4 proved it. So, but that's why I'm moving to ARM for my home server. Well, in fact, I've been on ARM for my home servers. 2017 was when I first put them up. 2017, yeah. And but what about the desktop? what are you doing with that? So yeah, that's really my biggest issue still. I mean, on the desktop, I've looked at Apple's M1 and M2. They don't have a whole lot yet out in the M2 side of things, but I've looked at the ARM single board computers, SBCs. I use an AMD desktop, although right now it's turned off because I'm not actually using it. And Intel desktops, I have an Intel-based laptop, and I use that as my daily driver. So, and it's also where I make these videos from. The other thing is that some of the work that I've done, and this is going back all the way to the Raspberry Pi 1 when it first came out. So, I've been at this a while. Can an ARM SBC serve as a desktop Linux device? That's really my question. Can it? Will it work? Well, here's what I found so far. So, yeah, this goes back, roll back the clock to, I skipped over the Raspberry Pi, mainly because the specs look like they just weren't going to be enough to even get started. It was a non-starter, basically. I mean, it's an interesting tool for makers and being able to do IoT devices and that kind of thing. It was to teach children how to program. I thought it was a great thing, and it was very inexpensive. It still is. Raspberry Pi 2 was really the first viable one to become a server. In fact, I used Raspberry Pi 2s for quite a while in my home network until they were supplanted. But it was too slow. The Raspberry Pi was just too slow to do anything on a desktop. Even with the Raspbian desktop, there was noticeable lag and delay. You could see it. But if you were just using it occasionally and for light loads, it'd probably be fine. But I don't do light loads. And the other one that came out just a little bit after the Raspberry Pi 2 was the Odroid XU4. And the Odroid XU4 was a pretty big step up from the Raspberry Pi 2. The Raspberry Pi 2 had 4 cores, the XU4 had 8, and it ran a little bit faster. They also had performance cores in it, so you could load up the first 4 with the high speed loads, and then the background processors would take over all the background tasks. Linux got pretty good. Now, at the beginning, Linux did not do a very good job of that, but eventually the Linux kernel caught up to the point where it did. And then Raspberry Pi 3 came out. That was pretty good. I mean, there was a little bit of a bump in the network speed, and of course there was a bump in the processor speed as well. But still, yeah, the problem with the Pi is it's tied to the USB and for the network speed, and they couldn't get above 200 megabits a second. It was okay. It was a little bit better for a desktop, but still too slow for me. Yeah, I'm pretty picky, apparently. Odroid N2 came out, and this machine was pretty impressive. But it was still a bit slow, and the problem with it was frame rate. I remember even on the Odroid XU4, the hard kernel folks, which manufacture the Odroid line, they had claims in there that it would handle. Now I don't know. They probably came from the CPU manufacturers, but I just can't imagine that they would be that careless about making claims like that. But that 4K video, 30 frames a second, it could handle it. No, it couldn't. Unless you consider handling it at a 40 to 80% frame drop as being successful. I wouldn't. But yeah, it would drop frames all over the place at 4K. HD worked fine, but yeah, 4K, no. N2 was impressive, but yeah, it was still a little bit slow. The main problem with the N2, the main problem with the N2 was it just didn't have enough CPUs to handle the load. It just didn't have the push. It was close, though. It was getting closer. Raspberry Pi 4, I remember people saying, oh, you could use this as a desktop. There are probably some people that use it as one. And with the Raspbian, it probably would be fine in light workloads. And it was getting closer for me. It looked like there was still some lagginess that was going on with it. especially with the operating systems I wanted to use. Raspbian's okay, but Raspbian is not what I want to use. I want to stay as close to my main machines here as possible. And I tried a number of them. I tried Armbian, and I tried Ubuntu, which they had one for that. Fedora came out with one as well. There was the NVIDIA Jetson. Now, I'm not talking about the small one. I'm talking about the AGX and the NX. Both of those are impressive. They're amazing performance, but those machines are geared toward doing AI development, artificial intelligence and development. So they're heavily purposed for artificial intelligence workloads, not for a daily driver. It works. It's ugly, but it works. Yeah, they were using Mate with a custom theme, and it was pretty ugly. It was pretty ugly. The main problem with those machines are the specialization. So if you're going to use it to do development for artificial intelligence, great. I probably would be a great machine to use as a desktop. Unfortunately for me, I don't. I don't spend all day doing AI development. I have some, but yeah, I don't spend all day doing it. Odroid N2 Plus. Now this was more like it. This machine is a beast, and yes, you could potentially use this machine as a desktop. In fact, I ran it for a while. I think I had a couple of videos where I was actually using it. But here's the thing with the N2 Plus. The only problem that it has is it doesn't have a native NVMe. You can plug NVMe into the USB, but no. I want a PCIe connection. I want a PCIe slot on the motherboard. So if I had that, well, yeah, it would be a better machine. Now, that's a 6-core machine. Odroid just released back, I think in March, into March, the M1, which is it's not an Apple M1, it's a Rockchip-based machine. It's a 4-core, and I'll talk more about it in when I get to the review section, when I do a review of the Odroid M1. But right now, that's the one I'm evaluating as a desktop replacement. So maybe finally we're here. I don't know. Maybe finally we're here. So, but I won't be able to do that review today. I'm out of time. So, but the next time I'll do a review of the Odroid M1, at least where I'm at with it right now. I mean, my review processes take a lot longer than just a few weeks. It's taken me, 2 months to just get one? Yeah, they were at, as you can, every time there's something that's shiny and new comes out, everybody buys it, and then for the next 2 months they plaster the forum with, I can't get this to work, I can't get that to work. One of the things I got to tell you. So, if I've been involved with a lot of these early adoption for these boards, there's always a struggle between they need to get the thing released to recoup their investment in the development of the board, and so they do not wait for every single thing to be developed. It's a work in progress. They will have their core set of operating systems, like for the M1, their core set is Ubuntu 2004 and Debian 10. Those are their core, but as you know, those are fairly old operating systems. And in fact, well, I think 2004 is still supported at least for another couple of years, but but here's the thing, you don't get the latest support in there, and so they have to make kernel modifications to add support for the drivers they need to be able to support the motherboard. And so and that's the real problem, is that those particular versions of the operating systems use a very old kernel. I think it's 4.4 based, which is the one they always use to make their initial changes. But here's what I was trying to say. So, you have to be patient with these guys, and and write it out a bit. It takes a while. And then eventually what they do gets back into the new kernels, and so you'll have full support of the drivers with the latest kernel versions. So yeah, that's just the way they do things. That's the way they do it. So some final thoughts here. I think, from the standpoint of a 10 gigahertz machine, is that possible? Well, anything's possible. Are we on a track to get there? Well, it's taken us 30 years to get to where we are right now, and I don't see it likely. It's possible, but I don't see it likely that we'll hit 10 gigahertz anytime soon. So yeah, that's the big problem. That's the big problem. So the Holy Grail is still going to be in pursuit for quite some time. A lot of people are thinking that that the architecture we're on is the problem. So now they're talking about the x86 architecture, saying that it's too old. It's basically has a lot of pieces that are retrofitted into it to make it modern, and the reason for that is there has to be a lot of care that's taken with processors like that, because they have a legacy, a long legacy that goes all the way back to the 8-bit and even earlier, the 4-bit days of computing. Now, I doubt that they really care all that much about being compatible with the 404, but there is still code in the world that runs on 8080 and 8008, so believe it or not. And so that code is still in the processor base that you have. So all that legacy is still supported, and you can't just re-architect. Now, Intel tried that. They tried to re-architect into a new processor some time ago, but that, I'm afraid, was a failure. The problem is that it wasn't the architecture. In fact, the Itanium is the one we're talking about. So they even made two versions of it. There was Itanium and Itanium 2. So it wasn't the problem with the Itanium so much. It was just that nobody wanted to move to it. It required some re-architecting of the software, and Windows kind of tried to support it for a while, but they kind of gave up, and then the whole project just faded at that point because no one was interested. And it was a good architecture. It was flexible. It would have been able to carry us forward, but again, the forces in the market held it back. So, and that's a problem. That's always been a problem when you're in a new environment. When they were in their new environment, they were the pathfinders, and they had a lot of decisions that they made along the way that have now cost them. It cost them dearly in being able to take advantage of new architectures. So it's not that the hardware can't change, but the support of the software absolutely cannot change. Because if that were to happen, then that would be a disaster. Again, no one would buy the thing. So that's my final thoughts. Then the other thing is, it's the heat barrier that's currently preventing us from going forward. So I'm gonna leave it there. Whether or not we actually get the 10 gigahertz or not, I guess time will tell. Hope to see y'all again real soon. Bye for now.